number 2 and number 3 in multiple regression. The good news is, as soon as we have that behind our back understood, then we're basically good to go also for, well, 90% of the stuff that we'll get after that. However, the tough part is, well, not so much that the things that I'm about to tell are so difficult on a piece-by-piece basis, but you'll get quite a few of these pieces, and they all look alike, so it's difficult to disentangle them in your mind. Okay, let's see. Does this still work? No. Okay, there. Yes, there we have it. One minor update, there was an extra change in the quiz of December 7th. This was the question where we saw 2 distributions, one totally skewed to the left or the right, I don't remember exactly, but it was totally tilting in one direction. And the other one looked pretty non-skewed to me, but if you took a ruler and you actually measured, and there was a 2mm difference between left and right. So I had no choice but to count the answer. Both are skewed as correct as well, even though I would think that one of them didn't look so skewed to me. But anyhow. Okay, we are here. All the stuff in gray we did. Step number 1 of multiple regression we did. We're now into step number 2, and there will be a step number 3 as well. These are the new commands that we're going to cover today. Whole state of stuff. The basic regression command gets an extra option called beta. We're going to use the predict, the recode command. You will see the OV test, frac poly or FP command we will briefly touch upon, and a command that's called df beta. That's all if I'm completing the whole slide deck in these 2 hours. So let's see how far I'll get. Okay, so this is the stuff that I need to get across. The same is for all the other ones. You have to think about your sample size before. In this case, for multiple regression, it's actually a bit easier, or actually it is more difficult, but for you it's easier because in the end, the only thing that I'm about to tell you is what a decent rule of thumb for the sample size is here. But we'll have to cover it at least briefly. Then, obviously, what you do in a regression run as well is before you do anything, you check your data for coding errors, so anything that's in the data that shouldn't be there. If you know that you have a variable female that's 0 and 1, and it has other values than 0 or 1, you know something's wrong. Then a larger part of the lecture today will be about thinking about which variables you need to include in your multiple regression. That will be a slightly more complicated bit. We already saw last time a little bit about running and interpreting a multiple regression run, and we'll do that a little bit more today as well. Then we end up with how to create new variables from the ones that you have. So you get data because you ran an experiment or survey or whatnot. The variables that you have, in principle, you can create new ones from those so that you have more to work with. That we're going to go through as well. Then a little bit about proper models. If our models in several different ways go haywire, then what can we do? And we have to check for outliers and assumptions, and I think for the larger part of this is the topic of the next lecture. I'll use 3 data sets throughout the explanation. The first one is the soccer data set that we have over there. That's also in the wikis. We have soccer data from the players from the World Championships in 2002. We had data on wine prices, where we look to predict the price of the wine based on the rainfall and the temperature in the summer or the winter. I don't remember exactly, but we're predicting at least wine prices. And there is no data for this part. This is a thought experiment where the idea is what we're trying to measure here is how anxious somebody is and how that depends on the size of a spider that we show that particular person. So we have, let's say, spiders in all sizes, and we show bigger and bigger spiders to different kinds of people, and we see what happens. Okay, so that's the data that we're going to go through. This was what multiple regression was. We're trying to predict a target variable y. Y has to be interval scaled, otherwise it's not multiple regression. And the predictor variables could be anything, either interval or categorical. If they are interval, you can, in principle, just add them to the equation. If they are categorical, you need to do more complicated stuff. You need to make separate dummies. If you have a categorical variable with 5 categories, you create 5 dummies and you include 4. That was all that we did last time. And also there is an epsilon there, sort of representing the noise. We're trying to predict y from these weighted sum of x's, but in all likelihood that won't work exactly, and we are left with a residual over there. Okay, so that was nothing new, all what we had last week. So, number 1, sample size. Well, the important thing, I'm emphasizing here once more, you do the thinking about it before you actually collect your data. Afterwards, it's typically too late. And you can end up in a real mess. If you have a sample size that's too small, nothing to do about it, and in the end you'll find nothing. And very likely that is, yeah, your sample is too small to find anything to begin with, so you could have just as well not do the whole thing. Calculating actual sample sizes here, in general, is way more difficult because you have to assume way more things about your data that you typically beforehand do not know. If I have, let's say, 10 predictor variables with which I want to predict some target, then I need to know all the correlations between all the predictor variables because that matters. All the potential correlations between my predictor variables and my target. There are lots and lots of assumptions there. Luckily, other people have done some work for us, and this is the summary of what they find. Here you see on the horizontal axis the number of predictors that you have, so the number of x variables, ranging here from 1 to 20. And there you see the required sample size on the vertical axis. And you see 3 non-greenish lines and a green line in there. For different sizes of effects. Obviously you see here, the one with the triangles. This is for small effects. Obviously if you want to find something that's small, you need a large sample. So there you see that sample sizes are typically high. Here you see sample sizes that are typically lowest. And that is for all the large effects that you want to find. Now generally I would argue that in social science research, the kinds of effects that you're aiming for is somewhere between small and medium sized. But it's somewhere between this line over there and that line over there. So I took the green one. And I roughly gave it the same slope as all the other ones. And if you see that this is the eventual conclusion of the sample size that you need based on different kinds of predictors, then for one thing you see that a typical multiple regression starts at 100 cases. So here and then upwards. So if you have way less, then you have reasons to be suspicious if this is going to work at all. It's not likely that you're going to find something, and in the end, if you don't find something, it can simply be the consequence, the direct consequence of the fact that your sample is too small. So if somebody forces you into a bachelor end project or a master thesis project where you are supposed to do some multiple regression stuff, but there is no data or not enough time to collect enough data, just don't do it. Do something else. And yeah, what I should say is the small print there. This is assuming that the population size is way bigger than the sample size. If you want to say something that is representative for some group of, let's say, 50 people, then a sample size of 45 is fine. Obviously, it's quite close to the 50 that there are there, but very often we're trying to say something about larger groups, and then you are stuck with that you need 100 or more. Okay, that's all about sample size in multiple regression. Easy, no analysis to do in Stata, just make sure that you know what the rule of thumb is. It starts from 100 and it goes up the more predictor variables that you have. Actually, the next logical one will be this one, before you start thinking about which variables you need to include, not only how many cases, but also which predictor variables that you want. But it's easier to do the third one first, because we basically covered this last time. This is a very brief recap of what we did before on the soccer data. So here, the first thing to do was check the data, and we would see that there are players in there who are claimed to be 245 tall, or 240 tall, which we really think is probably not the case. So what I do is I create a new variable, I call it length here, missing exactly where height is larger than 210. I don't think there are any players that are really that tall. Must be a coding error. I put a missing in there. I create variable h. H is handy because we had a birth here, and sort of coded the wrong way around. So I wanted something where I can see in the end, if I put the variable h in there, that okay, as a player gets older, does the player then also get taller? It would be unlikely given how old they are, but at least I can check. Then there was one categorical variable type, that is a player type number 4, goalkeeper, a defender, a midfielder, and a forward. So what I do here is I have 4 categories, I create 4 dummies, and here I do it using the recode command, creating 4 categorical variables: defend for defender, midfield for midfielder, forward for forward, keeper for keeper. And I could run a basic regression here already. And here, just to give you another example of categorical variable, I did something similar where I took the variable continent and then create dummy variables for South America, Asia, Africa, and Europe. And then you could again add these different dummies to the equation. Nothing new compared to last week. Okay, here you see, by the way, again, I add this only because there are different ways to do it. This I mentioned last time as well. If you want to create these dummy variables in a different way, it's totally possible. You can do it through this command, or through that one, or through this one. Have a look at the slides from last week. But the point is, you need to have these dummy variables in there. Here we see it. Here we have, let's see, a small example. I'm trying to predict length here from 4 dummies only, just to make the analysis a bit more concise and the table not that long. So I'm using 3 of the 4 categories that I have. Defense for defender, midfield for midfielder, and forward for forward. And I leave out 1, and that's the goalkeeper. So I now get results here, these coefficients, that are representative of the difference between these groups over there and the reference category, which is a goalkeeper. As you can see here, all these numbers, all these coefficients are negative, which is already suggesting that the tallest group of these 4 are the goalkeepers. If you know a little bit about soccer, then you also, I think, sort of know that in general the tallest ones in the field are typically the goalkeepers. There are a couple of exceptions perhaps, but not so many. And this gives us predictions for each and every one of the categories that we have, even though we have only 3 dummies here. I can predict now, well, for instance, for goalkeepers, that's a 1.6.533, and I can increase it a little bit. Minus 4.7 times, well, whether or not you are a defender, well, this is a goalkeeper, so there's a 0 over there. But also there's a 0 over there, because the goalkeeper is not a midfielder, and the goalkeeper is also not a forward. So this is the main prediction here for goalkeepers, 186.5. Same thing for defenders, and now the only thing that changes is, well, defenders have a 1 here, and a 1 for that number over there. So you subtract 4.7 centimeters, defenders are a bit tall, less tall, 182 roughly. Same thing for the midfielders, and same thing for the forwards. So this will give us a prediction for the average length of these different groups, and actual tests of the differences. And here you can see, by the way, from these numbers, all way smaller than 0.05, that all the differences of defender versus goalkeeper, of midfielder versus goalkeeper, and of forward versus goalkeeper are statistically significant. Okay, then something else. We could test in this table, the only differences that are being tested are the ones where we compare goalkeepers to something else, but we can compare the different groups that we have in phase 2. After the fact, we might test midfield equals forward. Let's see, midfield is 8.3 centimeters less on average, forward is minus 6.4 centimeters less. I can compare these 2 groups. Are they the same? And here we reject that base hypothesis. So apparently, indeed, there is also a statistically significant difference between midfielders and forwards. Okay, so that in itself is nothing new. One other thing that I mentioned here, I think I mentioned it in passing last time. One thing we didn't cover is the top right stuff over there. Here we are testing for this model, and this one has a couple more variables in there actually. Whether or not these variables here that are being used to predict the length of a player add something at all. And the HC0 is they add nothing, and that hypothesis is clearly refuted here based on that number, way smaller than 0.05. So the base hypothesis, you're not gaining anything here, is clearly rejected. Okay, so that was all basically old stuff compared to the last time. There's nothing new besides perhaps this in there. So, now the new stuff. We're going to try to find out the effect of which x here is largest. Because some of these are statistically significant. For instance, here, well, most of them in fact are. H is at the edge, and this one is not statistically significant. All the other ones clearly are. I'd like to get a feel for where, let's say, the bulk of the effect is. And one way to do that would be, well, be a little bit tedious, but I look at the r squared. It's now 0.6 or so, and I subsequently take out one of the variables and I check how large is my r squared now. If it decreases a lot, then apparently the one that I took out is really important. That would be one way to do it. The only thing is that if you have a lot of variables, it takes a really long time. Luckily, there's a better way to do it. First, the thing not to do would be to look only at the coefficients over there. And then look at, okay, which of these coefficients is highest. The coefficients themselves depend on how you have measured your predictor variables. So, for instance, if I see what we have here, if I would have measured age not in years, but in days, then for sure this coefficient would totally change, even though the model itself does not change. So you have to take into account what the spread of a variable is, and the way to do it would be, well, again, the standardization stuff. What we do is, for the target variable, we look at what it is here, length, and we subtract the mean and divide by the standard deviation. You get something now with a mean of 0 and a standard deviation of 1. We do the same thing for all the predictor variables. We take all these predictor variables, we subtract the mean, we divide by the standard deviation. Now I have in the end a standardized target variable and standardized predictor variables, and I rerun the whole regression with these standardized variables. Now, luckily, we don't have to do this by hand. This is what you get in terms of the coefficients if you would do that. The beta coefficients, is exactly the result of that exercise, and luckily, we don't have to do this by hand. So this is showing, after we have sort of put all the variables on the same scale, which of these variables then have the largest effect. And whereas we think here, well, midfield is quite a large effect here. This is 2.6 and this is 0.67. Here we see that if we look at this in terms of these beta coefficients, that in fact this one, 0.7, is larger than that, 0.2. And larger I mean in absolute value. So if this would have been a minus 0.7, then it would still be larger. Yes?
The fact that all those beta coefficients are between -1 and 1, is that a coincidence?
Well, yeah, depends what you mean by a coincidence. If you look at these coefficients, you have to interpret them slightly differently from these. Here you would say, okay, let's take age over there. A player who is 1 year older is in all likelihood, what is it? A little bit less tall on average. Okay, so you have a direct correspondence between an extra year gives me a little bit more or less in terms of y. Here it's slightly different. Here we have everything sort of translated in terms of standard deviations of the variable. So this is saying, well, if, let's say, weight gets 1 standard deviation higher, then the target variable, length, gets 0.7 standard deviations larger. And that means very often that these coefficients that you have over there are typically smaller than 1. Because it is unlikely, and a huge effect, if there would be a 1 standard deviation change in a predictor variable, and then a more than 1 standard deviation change in the target variable. So they are typically smaller than 1, or between -1 and +1, I should say, but they need not be. If you have a huge effect, there can be values that are bigger. Okay, so the thing not to forget is if you run a standard regression, don't look only at these. Try to figure out where the large effects are. You need that procedure here with the beta coefficients to make sure which is the really largest ones. This is still a little bit crude in the sense that this might work as long as you have interval scaled variables. So you have a variable that looks like this, and then you transform it a little bit, so you push it in a little and you move it so that the mean is now 0. Okay, you have sort of a similar variable that you can still interpret. This becomes more difficult with all these midfield forward, all these dummy variables, right? This is only zeros and ones, and subtracting the mean and then dividing by the standard deviation is not really obvious anymore what that looks like. But nevertheless, we do it just to make life a little bit easier on ourselves, and that gives you an idea of which of these variables are, in fact, the most important ones. And one other example here, just to show you that how it works. It works in the same way. We do not have any given variables there, so this is a standard auto data set from Stata. Here you see that I'm trying to predict the price of a car based on miles per gallon, weight, and the trunk size. You see coefficients there, minus 55 and 2 and minus 65. And there you typically see again, if you run the data option behind it, you see there. These numbers themselves do not say so much because in fact here the coefficient over there, 1.95, which is the smallest in an absolute sense from all the coefficients that we have, is in fact the largest effect. Because here we see that the beta coefficient is 0.5, which is way larger than all the other ones. Okay, that's the trying to figure out which of the components is adding the most part. Now, the more complicated one. Before you start collecting and analyzing your data, you want to think about which predictor variables you will need. This obviously typically applies when you collect your own data. And the stuff in yellow here, the experiments are usually somewhat less followed by that. And we're going to figure out why that is. So for a typical survey, you need to go out of your way collecting all kinds of predictor variables. And for an experiment, very often we need not bother so much. Okay, I need a couple of slides to try to bring that argument home. So you have to stay focused for a slide or slide 8 slides or so, I don't know exactly. First, something that I'd like to focus on up front. Okay, this is multiple regression. Not that multiple, you only have 2 predictor variables, but at least more than 1. So let's suppose that we have something here. And suppose that we have something here where the x1 is an experimental variable, something that we did in a lab that we created ourselves. For instance, think about that spider size. So we invite people into the lab and we have, let's say, 12 different sizes of spider. If you come in, then we randomly decide, okay, are you going to get the smallest one, or the slightly bigger one, or one bigger than that, and so on. So we randomly allocate you to a spider size, and then in the end we're going to measure your anxiety by, I don't know, collecting the sweat from your forehead, or who knows what, or we just ask. And then we could try to predict, okay, is spider size a decent predictor for how anxious you are? Okay, you can do it, then still it's not even multiple regression. Now let's assume that we have another variable there of which we think that it might be an effect, have an effect here as well. For instance, age. Let's say that as you get older, you get more accustomed to spiders, and then that effect is smaller, or who knows what. It doesn't matter so much. Now we have 2 variables in there that we use to predict: spider size, we created that ourselves, and age. Okay, so far so good. Now the claim that I want to make here, and that we will need in a minute, is well, first of all, if it's an experiment, then typically what we're interested in is not so much the effect of age. You may want to take it into account, but we're trying to figure out if this one is working or not. The spider size thing, does that have an effect? So we're interested mainly in only that coefficient, you could argue. And the other thing is, because we randomly allocate these spider sizes to people, it must be the case that the correlation between this one and that one is 0. You know, people are showing up at the lab and you get a spider size at random, so there is no reason for any correlation to be there between the age, between any kind of characteristic, in fact, of the person that comes in and the size of the spider that you get, because it's randomly allocated. Okay? Yeah.
Even though there shouldn't be any correlation, should you still check it? That it might be by chance a small correlation.
Yeah, if you can, you should. But very often you cannot, because it could be all kinds of characteristics that we didn't measure. And sample size, then the correlation between these two will be, let's say, close to zero, or close enough. Okay, hold that thought. Now for the technical bit. I'm trying to figure out here, how bad would it be if the real model contains two predictor variables, x1 and x2. Normally we do not know the real model, of course. And if I try to estimate that true model based on the true model except for one variable. So I miss one. So the examples here would be, let's assume that this is a real model. Y is equal to beta 1, x1 plus beta 2, x2. And I know here that first of all I'm extracting away from the intercept. There is no beta 0 here. Forget that for a minute. And I'm also extracting away from the epsilon. But let's also not be bothered too much by that. And what we do is we estimate this. So I forget x2, for instance, because I don't have it. And instead, I'm trying to estimate this y equal to, b1 hat, the predicted b1, x1. Now, if I run standard ordinary logistic regressions here, so a multiple regression, with one x, simple regression, then the b1 hat is equal to that. Just believe that. You can look it up in a textbook, it doesn't matter so much, but this is what actually is being calculated behind the scenes. Now let's see. If this is what is being calculated, then that is when we are predicting y from x1. Now let's see what that would give. That is by putting in there this equation, exactly that. So now we see that the predicted b1 that we would like to be equal to beta 1 actually is equal to beta 1 plus something else. I don't want that to be there. We would be fine if this would be 0. Or stated otherwise, we're totally not fine if this is not 0. Now let's see when that is. This part should be 0 and we are good to go for our estimate b1 hat. What does it mean that beta 2, if that is not equal to 0, that would mean that x2 is a decent predictor of y. If x2 is really predictive of whatever the y is, then that beta 2 is not equal to 0. And then we're halfway in the trouble because this part is not 0. And let's see what that is. Well, if this is predicting y from x1, then this is predicting x2 from x1. And so this part here is saying that x2 related to x1 is also not a good idea. So if there are two things going on, one is x2 is a good predictor of y, and the second is x2 is correlated to x1. If we have both of these, then we're screwed here, because then this term doesn't disappear. Yes?
But if x2 is a predictive of y, what's bad in that? Because if h is predictive of
Anxiety, yeah. Now, that in itself doesn't matter so much, but we care about it because I'm trying to estimate here through the b1 hat. This is the model I'm trying to estimate. And this is the wrong model because actually that is there. And if that is really there, then I get instead of b1 hat equal to beta 1, which is what I want, b1 hat equal to beta 1 plus something else, which is wrong. Right? Because I need to find only beta 1 there. Now, if this happens to be 0, so if age is not a very good predictor of anxiety, then the beta 2 here is 0, and this whole term disappears. We're home free. Or if this one is 0, and that is if x2 is not correlated with x1, then this thing is 0 here, we're also fine. But if none of these is holding, then we might be in trouble. No, not we might, we are. We're missing the true value by a mark. Okay, so we were trying to figure out which data do we need here. Well, the answer is basically on the previous slide, because there we saw what we need here is all the variables there that have two characteristics interested in, and they predict y as well. So if we have variables of that kind, we should include them. Okay, first let me show you that it actually works. I made a toy data set. One y variable and 4 predictor variables, x1, 2, 3, and 4. And I created a model myself here as y is the sum of, and then all this 2 plus 2 times x1 plus 2 times x2 plus 2 times x3 plus 2 times x4 and some noise. Here you see the correlations that I created. And you see here that y is correlated with x1, 2, 3, but not with 4. You see that x1 is correlated with x2, but not with 3 and 4. x2 is correlated with 3 and 4, and let's argue about whether or not this is a true correlation or not. But again, let's assume that I'm interested in the effect of x1. Now let's see what will happen if I leave out different kinds of variables. First we have x2 over there. No, let's start at the bottom. Let's look at x4. x4 is not related to y, and it's also not related to x1. So that extra term that we had will be 0. It was a product of two things. The left thing is 0, the right thing is also 0, so the whole thing is 0, so we should be fine. Leaving out x4 is not an issue. x3, let's see. We have here x3 is related to y, there's a correlation of 0.44, but it's not related to x1, there's a correlation of 0. Okay, so now I have that term. One of these terms is 0.44, which is not good, but the other one is 0, so the product of the two is 0 as well. So again, leaving out x3 should also not be an issue for predicting the coefficient of x1. And the only one that should be in trouble is x2 here. x2 is related to both y and to x1. So x2 is related to y, 0.31, and to x1, 0.8. So now I have that extra term where there is no 0 to be found, 0.8 times 0.8, and that will cause us some trouble. Yes?
Is it that you draw the line at 0.05 again?
No, I'm just trying to, say anything above 0.4 is, let's say, a decent sized correlation, anything below isn't. But it's not so much at exactly where the line is. So let's see. And here we have the results of 4 different regression analyses. Let's first look at the one on the top. I'm predicting y from all the variables there. So I'm exactly using the right model because I created it in such a way that that x1, 2, 3, and 4 are indeed predicting y. Now let's see here at these confidence intervals, you'll see that almost all these confidence intervals over there are just fine, and in particular, let's only look at x1 in this case, it is around 2. So if we look at where we are, we have a coefficient of 1.9 and a confidence interval around 2, which is good because all these coefficients were equal to 2. No trouble whatsoever, but this is still not a good example because here we are not leaving anything out. Here we have all the predictor variables included. Let's throw one out, x4. x4, we get rid of that one, and what does the model say now? Well, still we have about 2 as a coefficient, which is exactly where we want to be because the real coefficient is 2, and the confidence interval is nicely around 2. So again, this is fine. Sort of working. We now leave out x3, still okay. The estimate is now slightly above 2, but still close enough. And there we again have a confidence interval that includes the 2. So leaving out any of these two, x3 or x4, doesn't matter so much for the coefficient of x1. Finally, this is where the shit hits the fan. x2 was correlated both to x1 and to y. Leave it out, and now we get a coefficient there of 3.5, which is quite far away from 2, and we get a confidence interval over there that is around 3.5 and does not include 2 anymore. Okay, so leaving a variable out that correlates with another predictor variable that you have in there, and that correlates with your target variable, that is a bad thing, because it messes up the estimates of the other coefficients. Yeah?
So in the last one, let's say there was the mean was 3.5, but the confidence interval went from 1.5 to 4, then it would be all right.
Then I would still argue, yeah, it wasn't so bad. You know, we are off by a mile, you know, 2 versus 3.5, but still the confidence interval includes at least the 2, so that's perhaps not so bad. Yes? Well, I know that the true values are 2, right? Because it's how I make the model. So if I run that's different from normal. Normally I do not have a real model, but now I create one. Then at least what I want, well, I can phrase it in 2 ways. What I want is that, first of all, that the estimated coefficient is indeed near 2. But it's not so obvious exactly what near 2 would mean. You know, I'm near 2. So what I really want is that the true value lies inside the confidence interval that I estimate around that coefficient. That is one other measure of are we indeed in the neighborhood of the true value. So that's the only argument for that. Other questions about this? Okay. So, what does that mean? Well, if you don't want bias in your estimation of the coefficient of some predictor variable, be it spider size or anything else, then what you need is you need all other predictor variables that correlate with that predictor variable that you're looking at and predict your target. So one thing to do would be, if you run a survey and you're say, very interested in the effect of 1x on y, whatever it is in that survey, you need to think about which other variables also predict y and which other variables also predict x, and the ones that do both you should include. And this is also why typically surveys are long, because you have to think about a long list of other things that might also predict your target. And from that list, then check, okay, which one of these might be correlating with the other predictor variable that I'm interested in. And then you might even end up with, well, all. And then in principle, what you need to do is measure all these, which is a bit of a pain in the neck. They're a very long survey. Okay, now, the conclusion of that, well, this is why experiments are so powerful. Think about the spider size example. If I have spider size, and I'm trying to predict anxiety, then first I could think about, okay, which other things might predict anxiety? And I could come up with a huge list of other things that might cause you to be anxious. And then from that list, I'll look at, okay, which one of these correlates with that spider size variable that I just created? And the answer would be none. Because the spider size thing is randomly allocated to everybody, and there is no correlation with all the other stuff on the outside. And we need not bother about it. So this is why experiments typically have relatively restricted sets of variables that are being measured. Because the main manipulation that you're interested in is usually randomly allocated across all the subjects. And then you are home free. Yes.
What will happen if one x is correlated to another x but not to y?
Then, well, let's say if you have I have one predictor variable here, I'm interested in this one, and you have another one that is not predictive of y, but it is correlated to the other x, then you can include it. And what will happen, if you want, what will happen is first, this coefficient here will be 0, because it's not predictive of y. And this coefficient over there, let's say it was 8.5 before you had that one in, and now you put it in and it stays 8.5 here. So, you know, you could include it if you want, and then exclude it, doesn't make any difference. Okay, so, let's see that once more. This would be a survey like the spider example again. I'm trying to predict how anxious you get, and I predict this from, let's say, how often you watch Discovery Channel, the number of hours in a week. Because I have the idea that if you see more spiders on television, then you get rid of your anxiety, and then it might be different. That would be survey data. If I'm totally interested in trying to figure out what that E1 is over there, I need to collect all other variables that predict both anxiety and how long you watch Discovery Channel. I get a big survey. If this is the spider size example that I had, and I'm interested in this B1 now, okay, this correlates with nothing else. So for the estimate of that B1, there's no need to bother with lots and lots of other variables. Any questions about this? Okay, let that sink in. This is why experiments are so strong a method, and why there are so many parts of science where it's difficult to proceed. Because let's suppose that you have a survey, and you try to measure everything there is, and present what you find, and then always somebody can raise his or her hand and say, wait a minute, I think that there is another predictor for this target variable, and it is yada yada. And you didn't measure it. Yeah, then there's basically nothing that you can say other than, well, okay, perhaps next time we could include it and see if it makes a big difference, but there's nothing that you can say against it. It would be an experiment if somebody would raise his hand and say, listen, there's another predictor of the target variable that you're looking at. You could simply say, yeah, it might be, but that's not an issue, because the thing that I'm interested in is an experimental variable. It's randomly allocated across my people in the experiment, and every other variable should not bother with that effect. All right, so this is why experiments are powerful. There are no variables that correlate both with the target and with the extra with the control of the experiment. Let's see. No, I think that is the natural break that we need here. So let's see if I can use the couple more minutes before the break. Just to give you one example of all this correlational stuff and big data. The data that you will get is typically small scale, let's say at most a couple thousand cases, and that you will get at least in this course. I mean, later on you might get data that is way larger. But typically, if you have data that is, let's say, rich enough, you can find very unlikely correlations that are really, really high, even though it's totally obvious that if you look at it, there cannot really be any causal inference here. So there is a real risk in big data, because it is almost always possible to find something that predicts something else. There are quite a few more actually, cited. Two examples here, for instance, see the number of murders by steam, hot vapors, and hot objects actually correlates almost perfectly with the age of Missed America in a given year. I don't think there is a real correlation going on, and you see it changing a little bit in 2009. There was some kind of causal thing that made that the correlation went haywire, but you see here that there is looks stunning. If it would be something of which you had considered this beforehand, before looking at the data, then you would argue, well, this is a nice story that I had, because I had the story first, and then I look at the data, and then I find it. If you look at the data first, you'll find these, or this. The number of suicides by crashing of a motor vehicle is almost perfectly correlated with the number of Japanese passenger cars sold in the US. Again, I do not believe that there is a real causal inference here, and if the data is large enough, you can always find correlations like this that make it appear as if something is going on. Which goes to show that the most important thing, besides all the stuff that we do with the data, is think about what's going on. Okay, back in 15. So from the slide at the beginning, on that blue slide, there's a long list of things to do. And one of these things was, actually that was what I was trying to do, is I'm trying to figure out how many other predictive variables that I need. And I arrived at the conclusion, first, for experiments, it's relatively okay. Relatively okay means, well, if I'm interested in the experimental manipulation, I generally need not bother so much with measuring other variables that might also predict the target variable. However, for surveys, there it is a bit more problematic. There I need to think for a long time. And actually you have to think up front, especially if you collect it all yourself, whether or not all the variables that you need are included. Okay, for all the phone people, try to get rid of them. YouTube. Thank you. Another phone person over there. get rid of that? Thank you. So now we're trying to think about what it is that we need, and it's tempting to come up with as many variables as we can get our hands on, just to see if perhaps it predicts something. This is usually referred to as the kitchen sink approach. You put in as many variables as you can find, and then you shake for a while, and you hope that you find something. Well, as I showed you in the spurious correlations, if you have enough data to work with, then in the end you'll find something just by accident. So the best thing to do up front is really to think about what you would expect here, and focus only on the variables that you know or expect or suspect to have a true effect. So this do-it theory based is really important. And the other thing is, okay, as soon as I decide what I collect, I get my survey back, and then I get my variables in there. And I can create more of those from the ones that I have. The ones that I don't have, okay, they're out the window. But from the ones that I do have, I can create other ones to try to make, let's say, the most of what can be made from the data that I have. That second bit is something that we didn't do just yet, and that I will go through now. So we thought about the variables that we're going to ask for in our survey or experiment or what have you. We now get the data, we get rid of the coding errors, we look at the data and now feel, okay, at least this is all what has been measured. But from the ones that I have, I can create other ones as well. Now let's see how. There are a couple of ways. Several of these we have seen. One is if we have a categorical variable, we make separate dummies for each and every one of the categories. This is also, let's say, creating new variables from the data that you get. You get one categorical variable, you create 8 dummies, or however many you have categories. So that's one thing that we need to do, because otherwise we cannot use the categorical variable. Another one would be, well, if we just look at the interval scale variables, you might think up front or see from the data that a linear trend is not a very good fit for what's going on in this case. But instead, that for instance, the effect is not going like that, but is shaped like square root or log of x or 1 over x or what have you. Or x squared, you could try to fit a parabola through a cloud of dots and it might fit better than a straight line. So that's another way to go about it, and we'll see how that goes in a minute. And the third one is by what's called creating interaction variables. If I have 2 variables in my data, at least 2 predictor variables, I could in principle create a third one by, for instance, take the product of the 2. And when that will be wise, we'll see in a minute. Okay, so the first one we've seen already. The second one, let's look at that one. How do we do it? Well, the first one is you think about what the shape of the effect is going to be. So one example would be, I don't know, let's say the target variable is how happy you are. That's on the vertical axis. And on the horizontal axis, I have how much money I have. And I can imagine that, that in general, the more money you have, the happier you are. Let's take that strictly economic viewpoint. But if you think about it more carefully, you could see, well, perhaps in the beginning, extra money helps a lot. You get way happier if you have a little bit compared to close to nothing. And then at some point, it sort of tapers off. So this is, sort of square root or log of x might actually be better than just a straight line. But why it should be a log or a square root or a 1 over x, that's basically up to you. You have to think about, what is the x here, what is the y, and what do I think about what the shape of the effect is going to be. You create a variable and then you apply it. Okay, so that's the standard way to go about it. And one thing you should realize here is that in general, you don't want to have too complicated formulas here because it still has to be interpretable. So if you have, I do not see a reason why you would think that some very complicated transformation of x would actually be better. But you need to have a story as to why that would be the case, and then have a look if it actually worked. So all these you could simply create by hand and then see if log x is a better predictor than x itself. There is, and I'm sort of hesitant to show it, a sort of automatic command in Stata that is called frac-poly for fractional polynomials. And what it does is, if you do it, it tells Stata, try and find transformations of your predictor variables yourself. and then show what is the best that you could find within a certain range. If you say nothing, then say the default range. I think the default range is everything between variables raised to the power of minus 3, I think, to raised to the power of 3, and everything in between. And Stata will then show you which of these fit best, but you know, a couple of things could happen here. First of all, you can find all kinds of weird transformations that may fit better, but you do not know why. So this is really a weapon. So in the hands of a baby, there is a side command that's called FP, where the F and the P are this F and that P as well. Slightly different. There you look, if you have 10 predictor variables, one predictor at a time, with that Dec14 command, I'll show you on the next slide what it looks like. You look at all predictor variables at the same time. And it looks like this. So here you see the only thing that I change here in terms of the command, I type Dec14 in front, and what follows afterwards is just a standard regression command. In this example, this is the wine data. I'm predicting the price of a wine based on 2 rain variables and a temperature variable. Here you see, this may take a while, depending on, no, actually it's a small data set, so it won't take a while. If you have a big data set, this can take a long time. Here it comes up with transformations of the predictor variables that work better, where even slightly better is also counted as better. For instance, here you see that, well, the first 2, W, rain, and degrees, so that's, there we have it, these 2. These are transformed, but they're only, you know, the only thing that happens is the number is subtracted, so that doesn't make any substantial difference. You can forget about those. But here we see that H rain, there you see, what is that? X raised to the power of minus 2, so 1 over x squared minus 0.5. And there is a second variable created from H rain, that is x raised to the power of 3. And that's together, if we include these 2, is, according to Stata, at least a little bit better than what you would have if you just have H rain in there. Now, obviously, if you see this, only this, it's not so clear anymore what exactly the shape of the effect is, and if you want to get the effect of that shape, then you ask for a frac plot, and with frac plot you have to mention, okay, for which variable do you want to have it then? And in this case, the only transformation that made any difference here was that from H rain, and you get a plot, and now you see from the line on the graph over here what the shape of the effect now is. How is this different from the straight line? What you can see here as well, this is more or less also a straight line for the top of the graph. Here it is close enough to a straight line. And the only difference that this transformation is made is that it is adapting that bit here on the left to go up a little. So if you think this is important enough, then you might try, instead of H rain itself, the 2 transformations of H rain and include them together. Fine. In this case, I doubt if the effect is so large, but and in any case, not so easy to interpret. You know, it's only depending on, I think, that case over there. If you would get rid of that case, then this whole thing would collapse. But in any case, if there is a better fit for the data, then you can find it through that Dec14 command and its sister command FP. That FP command you have to check for yourself in Stata how that works. In principle, it does the same thing, but then 1 predictor variable at a time. Okay, so this, yeah.
How do you exactly know when you use a Dec14 command that it is a better result than without Dec14 instruction?
By looking at this one, you don't. So the only way to consider if there is if this is let's say, a real improvement, is by looking, for instance, here at the R squared that you have 0.72, and compare this R squared over there with the R squared that you had when you didn't do this before, so with the main command over there. But then you have to decide for yourself if it's, let's say, the extra bother is worth it. More questions about this? Okay. So that was the first 2, these dummies for categorical variables. Transformations of your predictor variable. Try a couple first. First think, then try a couple that make sense to you, and you could try to double check with that Dec14 poly command. Now, interactions. Variables x1 times x2. First, let's try to think about when we would actually expect these to play a role at all. And we can go back to the spider example here. So here we have spider size on the horizontal axis and anxiety on the vertical axis. What we have also is males and females in the data. The males are the blue line, the females are the pink line, and I'm sort of going with the prejudice here that, first of all, females get more anxious from spiders than males, and also the size of the spider has a bigger effect on females than on males. So let's see how we see this in the graph. First, this is anxiety goes up for males as the spider size gets bigger. Same here, anxiety goes up as the spider size increases. There is an effect of the difference between males and females. You see this from the height of the line. Okay? Here it's lower on average. About there. There it's higher on average. Okay, so the difference between the height of these two, that is the main effect of male versus female. The interaction effect is that effect here of the size of the spider. That's not the same for boys than it is for girls. You see this by the difference in the slope. So that different slope over there, that tells you, okay, the effect of the size of the spider is not the same for females than it is for males, just graphically. If you want to put that in actual equations, you could look at this. Well, this is the base model. I think that the anxiety is being predicted by the size of the spider. I think also that the extent to which this is happening, that is B1, that itself depends on whether or not you're male. Now, if that is what we have, okay, so that B1 itself is predicted, or can be predicted by the variable male, and we simply substitute one in the other, we get, well, first this, and that. So here you see that the substituting that B1 over there will call that the male variable over here reads the spider size variable over there, so we get male times spider size, a product of two variables in my data, as an extra predictor in the data itself. And I got it because I thought that, well, this effect that I had over here, the effect of one variable that I have in my data, that effect depends on another variable in my data. And if I do, I need to do basically two things. First, I create a cross product of these two variables, and I include it in the prediction model, without leaving out anything else, by the way. Okay, so, yeah, the only thing to do, you have to do this sort of by hand, like this. Create a new variable called, well, here I called it male times spider size because it's easy to interpret. Simply created by male times spider size. That's it. And this gives me another variable in my data. If I would test the actual model here with these interactions in there, and I would see, for instance, something like this. I get anxiety, this is the constant, 3.2, plus 0.9 times spider size, minus 0.8 times male times spider size. So that would mean actually that I predict for women this anxiety is 3.2 plus 0.9 times spider size. The effect of a spider size itself, as these things get bigger, anxiousness also gets bigger, 0.9 for every unit increase in spider size, and that difference is smaller for men, only 0.1. And that 0.8 that I estimated right there, so the thing that is in front of the interaction effect, that tells something about the difference in size of the effect. Yes? No? Was that a no? Was it yes? Not sure. Okay. All right. Okay, this is in a way problematic because this opens up lots and lots, perhaps too many, possibilities to create new variables. If I have 10 predictor variables, there are many ways in which I can choose 2 out of 10, and in principle I could try them all. And, well, a couple of things might happen. First of all, it might take too long to do it, and second, you might accidentally stumble onto something that is just accidentally an effect and not really true in the population. So you have to be a little bit careful here and make sure that you think again before you actually do this. which of these interaction effects would you expect here, and depending on that, try that one to see if it works at all. Something else that I want to show, but I'm sort of hesitant to do it because by showing a wrong argument here, I have the feeling that I instill this on the public and that it then more easier gets picked up as a right argument. Okay, what I'm about to say now is an example of what not to do. Okay, very often I see that, okay, I include the interaction of x1 and x2, could be anything in the data, because x1 and x2 are correlated. Okay, this is totally incorrect, that claim. If x1 and x2 correlate highly, that is actually is the last time where you want to include x1 times x2. The reason is quite obvious. If you have x1 and x2 as predictors and they correlate highly, then for sure, if I run a regression, the net effects of both of them will be relatively small, will be close to zero. Because the thing that I'm measuring is, okay, what is this one adding, given that that one's in there? Well, if they correlate really highly, then they don't add too much. And if I now create x1 times x2, so I already had two that were very much alike. And now I create a third one, which is also alike to the ones that I had before. Now I have three that are very close to each other, so to speak. Now I look at the net effect of this one, given that I have two other ones in there now that are alike to that one. So the effect in our likelihood will not even exist. But this is typically what you don't have to say here. If x1 and x2 are correlated, then you should get an interaction effect. No. The only reason is if you think that some effect of a variable itself depends on the value of another variable. That's the only reason that you can come up with. Males are less sensitive to the increase in the spider size than females, or the other way around, whatever. But that's the only argument that you need, and the only argument that works. Okay, let's see that correlation argument and why it's not working so well happening here. If we have a predictor variable in a model already, and we have something else that's really closely correlated to it, we might run into trouble. Let's see this here. I'm running a regression based on, this is again the standard auto data set, so what this represents doesn't matter so much here, but I'm predicting miles per gallon, so how effective a car is from the weight of a car. And you see here, yes, weight is a very good predictor of how many miles per gallon you drive. Also here on our square of 0.65, a highly statistically significant effect, so weight is a good predictor. And what I could also try is use length instead of the weight of the car. That also works rather well. Also highly significant, 0.0 nothing. Again, on our square of 0.63, so indeed, if I want to predict how many miles per gallon a car drives, this length variable also is a good idea. Okay, now let's see what happens if I include both. Now I include both weight and length here, and what you see is, well, now you see that the effect of length is no longer statistically significant anymore. Why is that? Well, multiple regression, we're measuring net effects. So I'm measuring the effect of length, given that I already take weight into account. Apparently, that length here doesn't add anything anymore if I have weight already in there. It happens to be slightly different the other way around. Weight remains to be significant. So if I know length, then adding weight still helps, apparently. But here, you might be tempted to think, okay, length apparently doesn't predict miles per gallon. It does, but it doesn't do it anymore as soon as you include weight. And why is this happening? Because the correlation between these two, between weight and length, between the two predictor variables, is actually 0.95. So you could argue, for all practical purposes, these two variables are more or less statistically the same. I can use either one. So this is also a reason to be sort of wary about including too many predictor variables, of which too many of them are alike. Those that are alike not only do not help you, but also sort of mess up your results. Could very well have been, in this example, it didn't happen, but this one here, which now still is in with 0.02, would have ended up being, let's say, 0.2 instead. So it might look that weight and length both do not help in terms of predicting, even though both do. Yes?
In here, length is not the
is totally independent of whether you type wavelength or length wave. The only thing that will happen is that these two rows will change, but there's nothing to do with these first. No. Other questions about this? Okay. So, the data, get rid of coding errors, all the variables complete, I create new variables from the existing ones, and you might wonder, okay, where does all this end? Yeah, the basic answer is it ends when you're done, when the whole set is complete. But if your data is quite elaborate, especially if you didn't collect it yourself, and it's not so obvious which variables to include, then there is a command that can help you at least a little bit. And this is the command that I need here. First I'll explain what it does behind the scenes, and then we'll go through what it means as soon as you do it. It's called Ramsey's omitted variable test, and that name, as we will see, is very misleading. Okay, what happens is, well, you regress y on your predictors. So you have already come up with 12 different predictor variables. One is a transformation, the other one is an interaction, and you run your regression model, and you see what happens. You calculate the predicted y, and I call that here y hat. We hope that y hat is close to the real y, but irrespective of that, we can create it in the data and call it y hat. Now I calculate y hat squared, y hat raised to the power of 3, and raised to the power of 4. What I do is I add these as a group. So I get 3 new variables in the data, y hat squared, y hat raised to the power of 3, and to the power of 4. I take them and I add them to the predictors that I had, and I rerun the model. And now I check, does it help to add these to the model at all? If they do, that is suggestive of that the predictor variables that I used are not picking up the variation in the y variable good enough just yet. So that is suggestive of, okay, you are trying to fumble around with these predictor variables, you've created an interaction, you've created a transformation, and now you hope that this command will tell you, well, good enough. And you have to check if this is the case. If it is, then it's no use anymore to try to come up with different kinds of transformations of the variables that you have, and you can stick to that model. If you find that this test says, okay, still not good enough, then you could do 2 things. One would be, from the variables that you have, try to come up with different kinds of transformations, or different kinds of interactions, or come up with totally different variables that you didn't include just yet, but nevertheless happen to have lying around, or can measure in addition, and add that one. So what the test does, and that is something that you have to realize quite clearly here, is given the predictor variables that you have you transformed them enough so that all the variation that we have in y is being picked up? And it doesn't say anything about whether or not you should include another predictor variable that you didn't include just yet, even though it's called omitted variable test. It only says something about, okay, I have 50 variables, and I took these 10. I transformed these 10 in a way that I think made sense, and I created a couple of interactions, and that's it. Now I run the omitted variable test. The omitted variable test will give me an answer to, okay, what I did here with these 10, was that good enough for these 10? It will not give me an answer, was there any variable omitted from the 40 that I left out? So in that sense, the omitted variable test is a bit weird. Let me see this happening. First, we run a regression. We run, this is again from the soccer data, but it doesn't matter so much. Here I didn't do anything basically. I regressing the number of goals that people scored based on their weight and their birth year. I didn't do any kind of transformation. If I run the OV test command, I see here that I have a test where the age 0 is what we added to one of the no omitted variables, and in this case, that is even supported. This is apparently good enough, or I should say differently, I can't do much better with these 2 variables. These are the only 2 that I will use. Second thing is that OV test command has 2 ways to do it. R please test over there stands for right hand side. This is related to the fact that you can do this in different ways as well. And the way in which I presented it was you had y hat and then raised to the power 2, 3, 4. I can do it on the other side of the equal sign as well. So I take all my predictor variables and I create predictor variable x raised to the power of 2, of 3, of 4. I add all these and see if that helps. That is what happens if I type here right hand side. And here you see my H0 is in fact rejected. So this would be hopeful, perhaps it's good enough, but this is saying no. That H0 here, that you have that is saying you've done enough with these two variables over there, where done enough, where I did nothing actually, is rejected. 0.01, below 0.05, so I have to keep fumbling with the two predictor variables that I have. So this is one way, to sort of a stop criterion. I tried as good as I can to come up with transformations and interactions. I think I cannot come up with much more. I run this test command twice, and this one has to be supported twice. And then I'm good to go. Questions about this? Yeah.
What was the H naught that you, again, you went over quite quickly in the last slide?
This one?
Yeah, so when you reject H naught, what are you rejecting?
Well, as it says here, that the model has no omitted variables, where omitted variable means this one, weight or birth year, in this example. You could put that in there in a different way, of course. Square root of weight, or add weight squared, or add weight times birth year. All these kind of things, we're testing that here if that makes sense or not. And the H0 is saying, okay, that wouldn't help. And that is supported here, but rejected there. Okay, couple of last bits. Ensuring what's called proper models. And that will lead in the end to something related to creating new predictor variables, namely creating a different Y variable. That could also be a good idea. Okay, for the rain data, it works like this. I'm comparing here the price of a bottle of wine to the price of a similar bottle in 1961. So the dependent variable in this case is the price of a bottle of wine divided by the price of a bottle of wine in 1961. So that means that by definition, I'm going to get a number that is above 0, okay, because I'm dividing by that price. Here we see a regression result, and we see here that, well, price is being predicted by vintage, the year the wine actually has in the market, with rain, breeze, and more rain, and some coefficients. I run my regression model here, and I have, in principle, estimated this, and this will give me a prediction for each and every case in my data, and, in principle, for each and every case that I do not have in my data, but for which you can give me the values of these. If you tell me what these values are, then I can give you a prediction based on this model. So let's see, if you want to predict here, the year of vintage is 2003, and 605 millimeters of rain in the winter, and the temperature was 16, and H rain, not sure what the H, harvest, rain during harvest time, that was 137 millimeters, then, okay, what? Let's see, a couple of ways to do it. One would be the tedious way, easiest to understand, but we wouldn't like to do it. And that is you type this by hand, you type in 12.7455 plus, and then, well, 137 times minus 0.001034, and just fill out the whole equation, and in the end come up with a number. And if you would do it, in this case, I did, then you end up with, in this case, 0.25. That's the prediction for this case. The other way to do it is slightly different. I have two other ways that I'd like to show. One is, here I have the same numbers again, and instead of actually typing these numbers over there, which is error prone, of course, also, I can simply tell Stata to do it, and access these numbers through _b and then the name of the variable. So this being the coefficient of vintage for minus 0.00802888, including all the ones that Stata still has in memory, but didn't show us. And then calculate that number. That would work as well, but still would cause you to have to type all this. And what I suggest you do, also to make sure that you can replicate all this, is include all this in a new file. And that looks like this, actually better. Here I simply first read in the wine data. I rename something here that's in capitals to something that is in small caps. I run my regression here, and I check how many cases I have in the data. It turns out to be 38 cases in my data. You can type count, then you see it, or if you can look at the spreadsheet that is behind the scenes, and then you see 38 cases. Now what I do is I create a 39th case that is empty in principle. Set observations equal to 39, and I now create the variables, and here I put these numbers for which I need to get a prediction. So I add in vintage is 2003, rain in the winter is 605, degrees is 16, rain in harvest time is 137, and now I rerun my regression model. Rerun my regression model, and now I add predict price 61 hat. So give me the predicted Y. And the difference that I have now is, now I created a 39th case. The 39th case didn't have a true Y value because it wasn't in my data, but that doesn't matter. This model has been calculated now on the 38 cases that I have. But this prediction command calculates the prediction for each and every case for which the predictor variables are there. Also the one that I didn't have in my data. So now I get also for the case that I needed the actual prediction given the model. And if you want to be nice and neat about this, as soon as I know this, first I type what I want to have, price 1 hat, vintage will be 2003, so in this case back, and also the prediction that belongs with it, and just to make sure that I don't make a mess afterwards with that variable, I now drop that 39 case. Okay, so this is a slightly different way to do it, but if you would actually do this, there are a couple of surprising things that you find. First of all, this is the best way to do it. It's reproducible and gives you accurate results. And what you would see if you would actually do it is that the correct answer here, given the model, is actually minus 0.09. So what I said was before, if you do this by calculator, this is 0.25. And this is because here there are quite a few numbers behind the 8, 9, 3, 6, 4, and 5 that data doesn't show you. And if you are unlucky, you might end up in a case where this is actually bothersome to you, and that 0.25 that you find by calculator is actually simply the wrong answer by quite a distance. The true answer here is minus 0.09. So, first thing to get from this is forget that calculator option. You don't want to do this. It's tedious anyhow, and might actually give you the wrong answer. So that's two strong reasons not to be willing to do it. And the second issue that we now get is if we do it the right way for this model, we see now we get a predicted value here of minus 0.09, and that cannot happen because the Y variable was price divided by price in 1961, which is necessarily above 0. So what can happen here is that if we have a Y variable that we sort of say interval enough, then it can happen that if the Y variable is bounded above or below, that you get a regression model that fits best, but that can predict for other cases values that you know cannot be right. We cannot have values below 0, and my best prediction here is minus 0.1. Okay, so to try to solve this is the standard way to do this is make sure that it doesn't happen before you actually run the regression. So let's see. I want to have that. No. This is sort of the higgledy-piggledy solution. The first one is you run your model, you create your predicted values, and you check your predicted values. Are all the predicted values, let's say, decent in the sense that they are never in a range where it simply cannot happen? So if you have a target variable that is ranging from 0 to 100, you will not get any predictions that are 250 because it simply cannot happen. That's one way to do it. That would work for all the cases in your data. You can check it there. But in principle, your model is supposed to say something about the population. And the variable mean that there are cases in your population that, for which you can get a prediction that is outside the bounds. So it's sort of a short-term solution, but not very satisfactory. Instead, just try this. If we, instead of the standard weighted sum of x's, we use not this part, B0 plus, and then all the way up to B and X. But instead, take e raised to the power of that thing. Then we for sure know that the y here will be larger than 0, because this thing here will be larger than 0. And another way of doing this is instead use the log of the y, then you have the log of y with this. So what happens here is, if you know that the cases in your data necessarily are larger than 0, then to make sure that you get predictions that are also larger than 0, you do this, you take the log of y, and then you run your model. And that will ensure that all things will work out. One thing you have to take care of is this one. Okay, here I do it. I take the log of y equals to log of y, where log in theta terms is a natural log, so there is no ln here. I run my regression, so I run here regress log of y, the thing that I now created, on x, over there. I predict my new variable, log y hat, and now I have to retransform my variable back to the original y that I wanted to have. I create y hat as e raised to the power of log y. I do this, so first I transform with the log, then I transform it back by raising to the power of e, and then in the end I get my y hats, and these are now all nicely positive. So this is one way to make sure that in the end, if you know that the number you were supposed to get is positive, that will actually work. You'll get positive numbers. Okay, one other trick from the same set. If you're predicting percentages or anything else basically that is bounded, really bounded between two values above and below, let's see how that works. Well, if we know that something is, let's say, between 0 and 1, we could try to estimate this. Y equal to, and then this model over there. That'll work in the sense that we know up front that this will always be between 0 and 1. Look at what happens here. If this thing, B0 all the way up to B and xn, that can change from minus infinity to plus infinity. If it is minus infinity here, you get 0 over there, or slightly above 0, so it's the left one. If this one goes to plus infinity, you get e raised to the power of plus infinity over e raised to the power of plus infinity plus 1, which is very close to 1. So then you are at that end. This will work. You do the math, you solve for q here, and then you see, well, the thing that you need to do now is you take instead of the y that you have, the log of y over 1 minus y. And that'll ensure that your model, in the end, nicely gives predictions that stay within the bounds of 0 and 1. And there's a wiki online where I ask you to try to figure out what you should do if you know that your data is not between 0 and 1, but actually between A and B, so in general. And what you then need to do is something similar to this, but not completely. Again, you're running in some issues here if you have real zeros and real ones, because all this is only working if the edges are not taken. So the percentages are never 0 or never 1. If they are, then the simplest solution, though a bit ugly, is simply change all the zeros to 0.001 and change all the 1 to 0.999. Okay, so this one I mentioned already. In the wikis you'll see that there is a question in there to try to figure out how this would work if it's between A and B. And